Okay, so hello everyone. I am Kostopoulou, a PhD student at Columbia University. And today I'm going to talk about caching in differentially private databases. But first, let me start the presentation with an example. Now, Citybike is a large service that provides bicycles available for rent in many places around New York. And the company behind Citybike collects data every day about users' demographic information or travel patterns, and then makes it available to the public. Doing that, they provide a rich source of information for people who can now detect trends about the users, the routes, or even the bikes, right? Now, however, in 2021, the company stopped releasing information about user demographics like age or gender. And this could have been possibly because of privacy concerns, of course. Now, this raises a question. Does Citybike protect the privacy of its users? Is this measure enough to do that? And the answer is no. Imagine a scenario where your neighbor spies on you from your window, and one day, they see you taking a Citybike ride, so they know what was your exact starting time and location for this ride. Now, it looks like if your neighbor combines this information with the Citybike records, they can actually infer what was your exact arrival time and destination. And in fact, we know that this can happen for 80% of all New York City rides, which is extremely creepy. Okay, so even with the little information that is left in the dataset, the privacy of users is still at risk. And the moral of this story is that Citybike, but also other services, must start releasing data in a more responsible way. And we have today the technology to do that. It is called differential privacy, or else DP. And intuitively, DP is a theoretical framework that lets us control how much information is leaked about an entry in the database when we release the output of one or more queries. So with the DP first, we allow queries that request only aggregate information over the entire database, like statistics, for example. And second, before we release the outputs of those queries, we need to add to them some properly configured noise so that we help hide entries that participate in the database. And now this is basically all that you need to know about DP theory for this presentation. Now, going back to our example, Citybike can leverage this technology by switching their infrastructure to a differentially private one, so they could use, for example, a DP database like Cumulus, Chorus, or Google DP. And the promise is that if they do that, when your neighbor analyzes the data, they will not be able to confidently learn anything about the right in the database that they wouldn't be able to learn if the right were not in the database to begin with, which is extremely cool. Like, DP is very cool, it's great in theory. It is the state-of-the-art solution for providing strong privacy guarantees, but it does suffer from a few challenges. And the biggest challenge of them all is something that we call running out of privacy budget. Okay, so you can think that this randomness that we apply on each query output essentially bounds information gain. And now, as we run many queries on the database, this bound accumulates across them. So, if we want to provide a rigorous privacy guarantee, there is a point after which it is essential that we terminate all execution and then discard the database that we have. Perhaps another more intuitive way to think about this is that the database has a privacy budget that is attached to it, which is what we call a finite resource. And then every query that is executed on the database consumes some part of it. And also, of course, the more budget the query consumes, the more accurate its result is going to be. Now, the issue, as you can see in this little GIF, is that current DP databases consume this privacy budget very fast. That is, before users manage to complete any useful analysis on the data. Okay, now our work, Turbo, aims to tackle this problem. But before I tell you how it works, let me first show you a demo. Okay, so here, you see that I am doing analysis on Citybike data using Grafana, which is a popular visualization platform. I split the screen into two parts, and I'm submitting the exact same queries to two different DP databases, one on the left and one on the right. Now, on the right side, I use Turbo, and on the left side, I use the baseline that we compared Turbo with in the paper. Each time I run 6 count queries that are broken down by different attributes. And the green histograms that you see here show the differentially private results, which in this case have been configured to have a relative error within 5% with high probability. Now, as I fast forward my work, I want you to focus on the lower part of the screen, where we have 2 graphs, one graph for each method. The x-axis shows the number of queries that I have submitted so far, and the y-axis shows the total budget that was consumed by those queries. So, of course, the lower, the better. Now, you can see that on the left screen, after only 30 minutes of work, my database runs out of budget, which means that I, as an analyst, can't use it again. But meanwhile, with Turbo on the right, you see that the graph somehow magically plateaus, right? Which allows me to continue my analysis on the database. Okay, so how did we do that? Now, the answer behind Turbo is caching. That's what you typically do in systems when you have a resource that you want to conserve. So Turbo is a caching component for DP databases like Humid Cores or Google DP. And it combines traditional caching with a differentially private mechanism that is called, in general, private multiplicative weights, or else PMW. And as you see in this little GIF, it helps conserve privacy budget by reusing the DP results of previous queries to answer new ones. Okay, let's move on to the core of the presentation and explain how exactly Turbo works. Turbo can be integrated into any traditional DP database. And the DP database typically comprises 3 components: a regular database that computes the result of the query, a differentially private executor which adds noise to that result, and finally, something that we call a privacy accountant, which we use to subtract budget for every query execution that we have. Now, Turbo is a 2-level cache that connects with the DP executor and the privacy accountant. The first level of Turbo is what we call an exact match cache. So this is a simple traditional cache that reuses a previous DP result for a query that it has already seen in the past. And you can imagine, obviously, that the performance of this cache depends exclusively on how many query repetitions we have in the workload. And here's how it works. Now, if a query comes and hits on this cache, then we don't have to pay any privacy budget, and we simply return the stored DP result back to the user. But if the query misses on this cache, then we forward it to the second layer. As we mentioned already, the second level is a PMW. Now, the PMW is a powerful differentially private mechanism that has been studied extensively in theoretical settings, but is hardly used in practice. The idea behind it is that it reuses past DP results to build an increasingly accurate histogram representation of the database. And there is this theoretical property of the PMW that says that the histogram is guaranteed to converge to an accurate state. And the cool thing now is that once this happens, we can use it to answer queries accurately and for free. And those queries don't have necessarily to be seen in the past. Now, before I continue, I should say that in this presentation, first, we will show that the PMW is extremely inefficient in practice. And second, we propose an alternative that helps us unleash its theoretical power. First, let's see an example of how the PMW works, though. Now, we start with a toy COVID dataset of 100 rows that has 2 attributes, positive and age group. Positive can take values 0, 1. The age group can take values 0, 1, 2, or 3. Now, this histogram is an equivalent representation of the COVID dataset. In gray color, you are able to see the real values of the bins, which of course we never release to the public. Now, these values are counters that indicate how many records of the database belong in each bin. So, for example, we have 13 people who tested negative and belong in the age group 0. So the upper left bin counter is 13. Now, the estimate values that you see in the bins are differentially private, so we can release to the public. And we generally be trying to approximate the real ones the more we use the PMW. And notice that at this point, the estimate values are inaccurate. They have all the same value, 12.5, because the histogram was just initialized uniformly. Okay, now, suppose that query 1 comes and tries to access the PMW cache. You can see that this query requests for the count of positive COVID cases, so it accesses the bottom row of the histogram, which is why also we have colored it green. Now, the histogram computes the result of the query by summing up all the estimate values in the green bins, and then the PMW asks the question, is this answer accurate enough? Now, to find out, the PMW will check in a differentially private way whether there is a big gap between the true result of the query and the histogram result. Now, this check is performed by a mechanism that is called sparse vector, which we will not detail here. So in this case, the result is not accurate because the histogram at this point contains random values. In caching terms, this is equivalent to a miss. The cache now has forwarded the query to the DP executor, and as you see, it has used the DP result to update the state of the histogram so that it brings the estimate values closer to the real ones. So if you noticed in the slide, the bottom row estimate values have changed. Now again, a second query comes, requests for the count of people in the first age group, so it accesses the first column inside the histogram. Again, the histogram computes the result, the PMW asks, is it accurate enough? Once again, the answer is no. So again, we run the query using the DP executor, and then we use it to update the state of the histogram. And now finally, query 3 comes, and it requests for the count of people who tested positive, but also belong in the first age group. So it accesses the bottom left bin. Notice that this query overlaps inside the histogram with the 2 previous queries, right? Now, we compute the answer of the query using the histogram. The PMW asks if it is accurate enough. And now the great news is that this time the result is accurate. Why? Because over the last 2 rounds, the bins have become more accurate because we updated them. So the 2 previous queries, even though they were not identical to Q3, have actually helped us answer Q3 for free, because this time we didn't need to call the DP executor. So this is how the PMW histogram works. Now let's zoom out to the system architecture again and show how the cache works in general. Okay, if a query hits in the PMW cache because the histogram prediction was accurate, then we don't pay any privacy budget, we are happy, and we simply return the DP result that was computed by the histogram back to the user. But if the query misses on the PMW cache, then we take the following steps. We run the query with the DP executor, we use the result to update both caches, and now, before we return the DP result back to the user, we must pay a painfully large privacy budget for all the operations that the cache needed to do, which is the accuracy test that failed and the DP execution. And in fact, this budget is 4 times larger than the budget that we would pay if we didn't have any caching at all. The reason we pay only when we fail the accuracy check is related to this sparse vector mechanism, which you can find in the DP literature. Okay, so given that every miss on the PMW practically costs a fortune, does this PMW work in practice? This is where we run a small experiment on a larger version of the COVID dataset with a workload that generally has a lot of overlapping queries. And these are the results that we get. So we compare the PMW with the exact match cache and with another baseline that doesn't use any caching at all. X-axis shows, again, the number of executed queries. Y-axis shows total privacy budget consumption, so the lower the better. And we see that the PMW manages to converge at about 7,000 queries, as it is expected from theory. And indeed, after this point, it spends very little privacy budget. But it spends an excessive amount of privacy before it converges, which makes it eventually worse than the exact match cache baseline. And you can imagine that this is, of course, because the histogram at first is untrained, and so the PMW spends 4 times the budget on misses. So the answer is no. So far, the PMW seems to be effective only in theory and not in practice. Now, these results raise an important question. how can we avoid the expensive PMW misses? The answer that we give is to bypass the PMW when it is not ready. So this is what Turbo does, among other tricks that we did not mention here. Turbo uses a module that we call PMW bypass for its second caching level. And the idea is that upon the arrival of a query, the PMW bypass will use a heuristic that peeks into the histogram and checks if it is well trained to answer that query accurately. Now, if the answer is yes, then we use the PMW, and in this case, if the heuristic was right, it means that we have a hit, so we pay nothing. But if the heuristic was wrong, then it means that we have a miss, and we pay 4 times the budget that we would pay without cash. Now, if the heuristic instead says no, we bypass the PMW, and then we directly use the DP executor. In this case, if the heuristic was right, we have saved ourselves a fortune, and instead we only paid X amount of privacy budget for the DP execution. But if the heuristic was wrong, then we just missed on an opportunity to save X amount of privacy budget. Our turbo heuristics intuitively count the number of updates we do to its bin inside the histogram. And then, for the histogram to be ready, all the bin counters that are relevant to a query must exceed a particular threshold. So this is a very simple idea generally, and it works very well in practice. But now bypassing, while it's a nice idea, it comes with its own implications in theory. More specifically, when we bypass, we must still use the DP executor results to update the state of the histogram. Otherwise, it will never get trained, right? Now, these kind of updates can actually spoil the PMW's convergence guarantees. Intuitively, you can think about it like that. If the histogram is ready to answer a query, but the heuristic is somehow mistaken and it says no, and therefore we bypass the PMW, the update that will take place might mess up with the already accurate state of the histogram and ruin it practically. So how do we solve that? We introduce what we call a safety margin, which allows updates to happen only when the distance between the DP result used for the update and the histogram is large enough, which is an indication for us that the histogram is not accurate at this state. Now, the PMW bypass is a new theoretical object with its own properties, which we study extensively in the paper. But I should mention here that one of those is that it achieves convergence like the PMW does, only at a slower pace. So let's see some results. This is how Turbo behaves in the previous experiment. It gives more than 15 times better privacy consumption compared to the exact match cache, and an even better improvement, of course, compared to the poor PMW. You can observe that it manages to bypass all the expensive initial training cycles of the PMW, and then it converges to an accurate state. Of course, we implement a few more tricks that make Turbo so effective, which we detail in the paper, and we provide a much broader evaluation of Turbo. We use the COVID and the city-bike datasets, and we also produce a variety of workloads by controlling the skewness of these workloads. And for all cases, we see that Turbo has significant improvement over the baselines. And also, another thing is that our work extends to streaming databases, but again, this is out of scope for this presentation. Now, we have integrated Turbo with Tumult, a state-of-the-art DP database that was used recently for the release of the US Census, and we publish details in an extended version of the paper on arXiv. And also, we open source everything in the link that is provided below. Okay, so what I'd like the takeaway of this presentation to be is that first we need to start adopting more responsible data release approaches. And while we have the tools to do that, they still suffer from major challenges. And on that note, we want to call on the systems community to use their own superpowers and help unleash more of differential privacy's theoretical power. Thank you.
Questions? Hi, nice talk. So there's Dimitri, ICL. So I understand you use the example of count queries, which make sense to model as a histogram.
Yes.
So you can prove the DP guarantees. I'm wondering if you have proven in the paper or you're planning to work on more complex queries that are not based on count. And if not, what would count enable us to do as a primitive in terms of queries?
So currently our work does support only counts, but in general, the PMW approach supports all linear queries that can be performed, on the histogram. So we plan on extending to more queries. Like this is our plan for the future.
Yeah, thank you.
Hi, I'm Zhu Tao Zhang from Microsoft. So you're talking about the privacy budget for the original privacy database, right? I just wonder why do we need this privacy budget and what's the overhead of the privacy budget in the original privacy database? So, yeah.
Why we need the privacy budget?
Yeah, so what's the overhead of the privacy budget? So why does it, why can we have an infinite amount of privacy budget?
I'm sorry, by overhead, what do you mean?
Infinitive amount of a privacy budget.
Okay, so that comes from the theory of differential privacy, right? And I kind of gave the intuition. Like, suppose that you have a query and you add some noise to it and then you run it again and again and again. By collecting all those results, if you do some kind of variance reduction of them, you will be able to approximate the true result. So in that sense, there is a point where you have to stop the execution. This is what the privacy budget intuitively tries to quantify. Yes, so this comes from the differential privacy theory, basically.
Okay,
you can't have an infinite privacy budget.
Yeah, thank you.
You are next. Go ahead.
Okay. Eli Margolin, University of Pennsylvania. Really cool work. I was wondering if you could speak a little bit about the heuristic that you all decided on. And like you mentioned, it's like very simple and works really well. I was curious just kind of if you tried things that were more complicated, did you find that they worked better, worse, and how you think that complexity could impact the training?
So we experimented with two big categories of heuristics. One is when you impose a counter on the whole state of the histogram, and one where you impose little counters on every being separately within the histogram. So we provide a broad evaluation of both the heuristics in the paper. We think that the second one is better. We call it an adaptive, self-adaptive heuristic, because you're able to start with a first configuration of your parameters, and then it penalizes itself as it makes mistakes to increase that threshold, so that it is harder for you to exceed it, and so that you bypass the PMW in the meantime. So a very naive, basic intuition is during the first steps, for example, the PMW, it's untrained, so I better wait for 100 rounds till I first use it. That is the first type of heuristic, which is kind of naive compared to the second one.
Awesome. Thank you so much.
Do we have time?
Nice talk, Stefan Soroyo, Microsoft. So, if I understand this correctly, the effectiveness of your cache now depends on the order of the queries.
Yes.
And I was wondering whether you've done any sensitivity study, how sensitive is to the order of the queries? In other words, if I submit the queries in a slightly different order, will the behavior change a lot or just a little bit?
Slightly different.
Because I imagine a lot of these queries, their order is not that important.
Yes.
I mean, sometimes, obviously, it depends on, yeah. So in that case, is there an opportunity to think about what's the order in which I submit the queries to the system? And will that really make a difference, a huge difference in practice? Because it will make a difference, but I don't know, it will make a little bit of a difference or a lot of difference?
So we don't explicitly evaluate that in the paper, but in theory it should make a practice. For example, if you have a workload that initially has a lot of variety in the queries that it uses, then you kind of train the histogram in a uniform way, right? Which makes it gracefully come to an accurate state. This is important. Suppose, for example, that you choose a workload that is very skewed, you pick the same query again and again, you train like only one small region of the histogram. So you pose another completely different query in the future, and the histogram cannot do anything. It's going to fail. It's going to miss.
Cool. Okay. Thank you for the intuition. Yeah.
Okay, let's thank the speaker.